Sorry about that. No, I'm recording. Okay. So if we look at this, you had these two pieces of material. You had the cylinder that had one density and it was a volume. And then you had the sheet of material that had an areal density. So there's no real difference in the way you approach it. You assume that the thickness is negligible, so you don't have to worry about it. That's why I gave you a density per centimeter squared. So first thing is to make sure that you convert correctly. So you want to remember that if you square a millimeter, then you have to, that's a factor of 100 in terms of, or 100th in terms of square centimeters. And I saw a few people that didn't have their unit conversions correctly, or they mixed them up. So that's always something you want to be careful of. And then the next thing is, once you find the area, so for parts 1 through 4, the area is just in centimeters squared. And then for the cylinder, it's in centimeters cubed. Now I just chose to convert centimeters because of the fact that the densities were in those units already. And then you just multiply those out by the respective numbers, and then you get mass. So once you have masses, then the fact that they're different densities is no longer an issue, because now what you do is you just sum up the masses, as I see here, and then you go ahead and you get your Y bar and your Z bars. And you want to remember that, where's the origin? The origin's up here. So that means that 1, 2, and 3 are all negative in terms of their Z bar. The Y bars are 0 in some cases. And then you have the Y bar times M, Z bar times M. And then you go ahead and you add them together and get your respective answers. Okay. Any questions on that? Okay, good. All right, so that's the quiz. So next problem was a moment of inertia. And I just want to talk about that problem, and then I'm going to solve it for you. But I'm going to use Excel again on that one. But there's a couple things I want to point out with this. So when you're doing a problem like this, I'm going to go ahead and switch to the document camera. So there's what we have here. Now, what I did is the easiest way to do this problem is to take this whole 8 by 5 rectangle, start off with that, and then subtract off these individual triangles. I mean, it's not to say that's the only way to do it, but for me, that's the easiest way to do it. I guess another way would be to, you could draw a line down here and make 2 triangles, but they're kind of funky shapes. And so in terms of doing, so for example, if you were to draw a line down here and you're trying to find it about an X bar, there's no parallel X line here. So then you'd have to essentially, what you'd have to do is you have to draw a line here. And then let me show you, if you want to do it that way, you'd have to go, you draw it kind of light. So you'd have to make it into 3, this, and this. That's the only way that would work. So, but I chose to do it the other way. But you have choice. There's more than one way to skin a cat, or fry fish. So we go ahead, we have 1, 2, 3, and 4. We go ahead and separate them out. And then the next step, of course, is to identify the moment of inertia of each piece, and then add them and subtract them, and you're done. It sounds simple. Now, one of the things about this problem is that when we separate these out into our different pieces, is we just want to make sure that this is, in this case, we're finding IX bar and IY bar. Sorry about that. I should say, what are we trying to find? So we're trying to find about the centroid. So if we're trying to find it about the centroid, then first we have to figure out what is the centroid of this piece. Now, if I determine that, and again, I do that by just separating it into those 4 pieces, and then doing the centroid equations like we are experts at this point, I find that my X bar is 3.0 0.69, and my y bar is 2.15. So now I can draw my respective x bar and y bar. Now remember, when you're doing a moment of inertia about the x-axis, so this is the ix that we're talking about. We want to go about this x-axis here, because this is our centroidal axis of the entire object. So we know that ix of this is going to have to equal ix1 minus ix2 minus ix3 minus ix4, right? Because we're going to have to essentially take the whole rectangle and then subtract off those other three respective pieces. Now, for each, so let's look at one single piece. And I think the reason I'm pointing this out is because this is sometimes an error that can be confusing. Each piece, now, if we take, like, let's say we look at ix1, okay, that represents rectangle. So let's look at a triangle. We'll actually look at ix4 here. So that's this triangle right here. Okay, so ix4 equals ix about its centroid plus ad squared. Okay, so that's the parallel axis there, right? Ix bar plus ad squared. Okay, and so what we want to do then is we know that for a triangle, it's going to be equal to 1 over 36 bh cubed. And so the bh cubed is base times height. And so we know that in this terms of x, we know that it's the base is going to be this distance here, the 8, and the height is going to be the 2 inches. So we can get that. But this is just for this triangle about its centroid. All right. And then the ad squared term, of course, is the area of the triangle. So that's 1/2 base times height. And then the d squared. So what's the d squared? The d squared is this distance. So it's the distance from the global centroid, 2.15, minus the distance of this little centroid of this individual piece. So it's basically the distance from the global centroid to the centroid of the individual component. So 0.67. And then that whole thing is squared. So it's a times d squared, not ad and then squared. All right. So that's the 3. And then, so what you end up with is, hold on. What you end up with then is, go ahead and go to Excel. Is you end up with something like this, okay? So what I did, so backing up, what I did was I found the centroid. I used Excel for to find the centroid, like I did in the quiz. So I got my centroid, which I showed you. And then I went ahead and I did this, where I have my parts. I have part 1, 2, 3, and 4. And then I have the respective moment of inertia. So for example, if I go and I look at the square, it's 1/12 bh cubed, because that's what it is for rectangle. And then the respective triangles 2, 3, and 4, they are all as negative because I want to get rid of them. But I have to put them in correctly, 136 bh cubed, and so forth. And then so for IY, it's the same equation. You just have to flip the orientation. So the important thing to remember is when you're finding IX, you use the Y bar distances. And when you're finding IY, you use the X bar distances. And that's the difference between the two. All right. And the good thing about this is you can go ahead and you can then calculate AD squared in Excel, and you can add them all up And then your final answer is just the sum of those. So I have my IX, so 64.67, and then I add negative 47.08, and I get essentially 17.58. And that's my answer for that, and then my answer for IY. So this can help you if you use Excel, but it's not as it's not as tedious as writing it all out. It's better to write it out the first few times you do it so that you understand the process. Okay, any questions on this? All right, good. Let's go back.
One quick question.
Yeah, sure.
How do you want, when we're submitting Excel sheets, do you want us to just put a PDF and attach it? Or how else do you want us to go about attaching our work for homeworks with the like naming schemes and all that?
So if you want to use Excel to do it, then you can just do a cut and paste of the sheet. So kind of like what I did in here. When I solved this, you see, here's how I did my centroids, right? And then here's how I did the moment of inertia. And I chose to show it in Excel. So just cut out this piece that you have and it shows it, and then just paste that. And then I can see your numbers. I don't have to see the equations because I can pretty much surmise because I don't grade homework for accuracy. I grade for, the effort. So, and then if you've made a mistake, I could see it right away.
When you say paste it, you mean just put it at the bottom of our PDF, so same document?
Well, for example, if you were doing your homework in Word, you would normally you would write out your problems on paper, right? And then you would scan them. So if you were doing this, then you could just scan it and then insert it into that page.
Okay.
That's all. Yeah, okay. I mean, because when you're scanning, you could just as well scan. You could insert that and then have one. Do you guys? I mean, do you have scanners or do you just use your phones for all this?
The phones have scanner apps, okay, and so they act like scanners.
So I mean, I guess you could scan the screen, but it'd probably be easier is once you have the PDF to just insert another page with this on it.
Mm-hmm. Okay.
As long as I can see it, as long as I can, I'll leave it to you to figure out the logistics. But as long as I can read it and it's legible, then that's what I'm looking for.
Okay. Cool. Thank you.
All right. Thank you. Okay, so that's moment of inertia. So I did that example. There's one more example in your lecture you can look at, but practice a few of these. They should be pretty solid with them after you do it. And so for the final, usually what we do is we throw it all depends on what we choose to put on the written part of the final. But you could have a moment of inertia problem where you have both a centroid, and then you find the moment of inertia about that centroid. That's kind of a typical way that we check that you understand both. But it's again, you're going to see this if you guys take CU204 next year or in the summer. You're going to see this right away. This moment of inertia stuff. Okay, so let's talk about trusses now. So that's chapter 6. So for chapter 6, we have 3 things. We have trusses we'll start off with, and then we have frames, and then we have machines. So the trusses, they're at first they might look intimidating, but they're actually not that bad because they consist of a collection of 2 force members. So with that, that each member is either in tension or it's in compression. So, and the direction of the force is always along the direction of the member. So and we're only going to deal with 2D trusses. We're not going to do 3D trusses. So all you really have to be able to do is recall your summing the forces in the X and the Y and the layouts of the trusses, and you should be fine. I think actually one of the challenges with trusses is the geometry, because not all trusses have really nice equal angles and nice triple triangles. Sometimes they get pretty hairy, but if you could do the geometry, then the statics part isn't that bad. All right, so as I was saying, is if you think about a two-force member being in tension or compression, then the best way to visualize that is if you take a pencil and you hold it in your hand, like say you hold your hand. Let me do this. There we go. Could you see where you were seeing Excel all that time, weren't you? When I was talking there? Yes?
Yeah, we see it.
Okay. Now you see this screen, right?
Yep.
Okay, thank you. I just want to make sure. All right, so if you take a pencil like this and you hold it, now if I push in with my hand, I can feel the pencil point poking into my fingers and I can feel the eraser poking into my fingers. So essentially what I have is I'm compressing it. So since I'm compressing the pencil, both ends look like that. They're both pushing away, okay? They're pushing toward the joint. So if this was a truss, and these are my two ends, then if it's in compression, it's gonna look like that. It's pushing against. Whereas if I were to glue my pencil to my hand and try to pull it apart, then what I would feel is something like this, where it's pointing away. And so that's tension. So if I have the same member, like a member down here that's pointing away, it's going to point away on both ends. So that's going to be tension. That's going to be compression. All right. So that's what I was getting at there. Now, if we look at the different shapes that we could see. So going back, let me go back to this real quick. Slide. There we go. So if we go back to this, these are different shapes of trusses, and they're just different geometries, but they're all solved the same. So if we go now to something like this, what this shows you is how and typically you'll start off when you're solving a truss in a corner. And so what I mean by a corner is this is where the truss is supported, and then there's two members in that corner of the triangle. And what's nice about this is you can form a forced triangle. And if you know this and you know the geometry, as in you know the ratio of AF and AB, then you can use those ratios to solve for these forces. And that's a quick way to get this corner values. And then once you know those, because you can only solve for two unknowns at a time because you only have the two equations, some of the forces in X, some of the forces in the Y. So if you couldn't just start, like say, if you went to the middle of the truss where you had something like this, where you had 5 different unknowns, even if you knew 2 of them, you might have 3 that you didn't know. So typically with the trusses, what you're going to do is you're going to start in a corner. And so this is the one I want to look at today. So with this truss, we have an 8,000 pound, a 3,000 pound load up here at B and C. And we see that it's 8 feet tall, 6 feet between members. And so this makes a nice 3, 4, 5 triangle in terms of its ratio of X to Y. And then if we look at these respective parts here, A is pinned to the ground with something that can support a force in the X and in the Y, whereas E is only supported by something that can support a vertical load, but no horizontal. So E is free to slide side to side. And the reason this is done this way is because otherwise this truss would be statically indeterminate. And we don't talk a lot about that in this class, but that is something that when you guys go on to C204, you'll talk about statically indeterminate objects and how to solve for them, but we don't do that here. So we would, if you imagine if E was also bound like A was, and let's say you applied a force at D that had a X component, then all you could say was that AX and EX plus whatever the X component at D was equaled 0. That's all you would know, but you'd have no way of solving for AX or EX. So that makes it what's called statically indeterminate because you can't solve. Anyway, so we go back to this. If we're going to solve this truss, if we start up here at B, we have 1, 2, 3 unknowns. If we start at H, we have 4 unknowns. So we can't really start at either of those points. That's why we always want to start in the corner. Because if we start over here, we can determine what the Y component is of A. So we know A's Y component, we can determine that. Then we can solve BH with a triangle. So let's go ahead and look at that. So there's our truss, okay? So first thing we want to figure out is what is AY and what is EY? And so if we know that, that's always going to be a positive thing. And so if we sum the moments about A to 0, then, and we make clockwise positive, then what can we do? We can say 8,000 times 6, because that's the distance from there, plus 3,000 times 12 feet, 6 feet, 12 feet, and then minus EY times 24 equals 0. So now we solve and we get EY equal to 3,500. And now we know that EY, sum the forces in the Y to 0, we know that AY plus EY has to equal 11,000, has to equal the total of 8 and 3. So therefore we can solve and we know that AY is equal to 7,500. Okay. So that's what we want. We wanted to know what AY was because we're going to start on this side and move our way over. Now, I did send you a document last night that has this problem on it. And it also has a little box in the corner. I sent it out with the announcement. It had the moment of inertia problem and it had this, but it had a little box that I put on there that it looks like this, where it has the member. And then so it'll be, A, B, AH, so forth. And then it'll have the load, and then it'll have T or C. Sorry, it's kind of squished up there, but T or C, meaning tension or compression. So if you have tension or compression, that's what you want to indicate anytime you're doing a truss. You want to either put a T or a C to let the person know what that is. And then the load, of course, is whatever that value is. So now that we have, the first step is always going to be to find these reactions if you can't. And so if I had put, like, say 8 kips over here, and then so that would have made it 19, then we could have assumed by symmetry that EY and AY were equal, right? We would have just divided the 19 in half and been good. But because it's loaded more on this side, it makes sense that AY is going to carry more load than EY is. So let's look at joint A, and that's why we call it the method of joints, because we go ahead and we start at one joint. And if we look at joint A, what do we see? We have, here's our joint as a dot. We know that we have AY. We know that we have AH. And we know that we have AB. All right, so all those are pointing. Now, if we look at this, we know that in one of the big parts of trusses is that each of these are in equilibrium. Okay, so each of these is in equilibrium. So if this is an equilibrium, then that means that if I point AY up, AB has to be going down, because otherwise there's no vertical component to prevent this from moving. So that points down. Now, if that's pointing down to the left, AH has to point to the right. So now that whole thing's in equilibrium according to that. So if we then take the ratio of this, we can draw a triangle where we have, this is AY, that points down, that's AB, and that points over, and that's AH. And that's just like the forced triangles we talked about earlier in the quarter. So now we can just use the ratio. So we know that this is a 3, 4, 5 triangle, right? That's the ratio. So we can say now AY is to 4 as AB is to 5 as AH is to 3. So if we go ahead and plug in AY, 7,500 pounds, into there, we can solve for AB. And so we get AB equal to 93.75, and we know it's in compression. And we get AH equal to 56.25, and that's in tension. Okay. Does that make sense so far? So we took a simple truss, the simple 3, 4, 5 triangle, 6, 8, or 3, 4, 5. And first we figured out AY by summing the moments about A. And so our only unknown was EY. And then we know by looking at it, AX is 0 because there's no other force there. So AX is 0. So we go ahead, and if we draw our joint A, now if AX weren't 0, we would have had to have included that. But because then I guess I shouldn't have skipped that part, but I got ahead of myself. But yeah, if AX was anything but 0, you would have to include that here. But we didn't because it was. So we have AY, and then we have these, and then we just shape it as a triangle, solve by ratios, and we're done. Okay, so that's our start. So now we need to go, and if we go over to H, well, we could go over here, but we have 1, 2, 3 unknowns, so that's not going to work. But if we go up to B, we know AB, so we just have 2 unknowns. So let's go up to B, and now we can solve for BH and BC. So I'm going to draw a line. And again, if we go up there, we'll draw B. We know it has 8. Let me just draw this real quick. 8 kips. BC, BH, AB. Okay, so there's that. Now we know that this is in compression because that's what we determined earlier. So we know AB is in compression. Now we know that AB, if we look at it, sorry. Ran away with one of my pieces of paper. The dog ate it. Doesn't matter. So we know that we have 8 kips and we have that. So then the question is, what's what? Well, I know that AB is 93.75, okay, going up. So is 3/5 of that more than 8 kips? So because again, we want this to balance. BC is vertical or horizontal, so it has no bearing in it. I think that AB, the vertical component of this is less than that. So I'm going to say BH is going up that way. This one's easy, right? Because if this is going to the right and this is the only other X component, it has to be going to the left to balance it out. So if we go ahead and sum the forces in the X, actually we'll start with the Y direction to 0. Then we know that we have negative 8,000. And then we have, in this case, we have negative 8,000 plus 4/5 AB, and then plus BH equals 0. So essentially I have negative 8,000 plus 4/5 of 9375 plus BH. That equals 0. So this turns out to be 7,500. So therefore BH is equal to 500. Now, because 500 pounds is not negative, so what I mean by that is if I had guessed incorrectly, if BH was actually pointing down instead, then this number here would have been negative, and that would have told me I was incorrect. But because it's positive, I know I was correct. So 500 pounds in compression. And so I know that one. And then I go to BC, and if I sum the forces in the X direction to 0, then what for BC, it's just going to be what? It's going to be 3/5 of AB minus BC equals 0. So 3/5, again, AB being 9375 equals BC. And so BC in this case is equal to 5,625 pounds, and that's in compression. Okay. So that's how that's done. And then if you wish, you can then move to another joint. And so at that point, let's go back to this. So we've gotten, now we know this and this. Now, if we went over here, we would still be missing this and this and this and this. So we couldn't do that. So let's go down to H. All right. Now, interesting. Let's go to H real quick, and then I want to point out something. So if we go down to H, then H looks like this, doesn't it? You have this pointing down. That's BH. And then you have this and this. Now we know that AH is pointing away because that's in tension, right? We don't know the direction, but let's look at BH. Now, if this is the only one with the vertical component, so if that's going down, doesn't this have to go away? So that has to go up so that those vertical components cancel. And then we don't know whether this is in tension or compression. Let's say that I say that this is in compression. All right. I don't know it or not, so I'm just going to guess. So that's HG, and this is HC. Okay. So here I have my respective components for H. So this is joint H. All right. Okay. So again, sometimes you can solve these by inspection. Other times you, in some cases, you may have to do 2 equations, 2 unknowns. So far, we haven't had to do that. We could solve one, then just plug it in the other. But there will be times when you'll have to algebraically solve, which isn't a big deal. You guys have done that a lot. But so let's go ahead. We'll first sum the forces in the Y. We'll live on the edge. You can sum the force in the X if you want, or you can live on the edge and sum the forces on the Y. So we have negative BH plus 4/5 HC equals 0. And since we know BH, we can then right away, we know that HC is just going to equal to 5/4 of BH. And since BH we know is what, 500? So we plug in 500. So HC is going to give us 625 pounds, and it's pointing away, so it's tension. Okay, so we're happy with that. So then now let's sum the forces in the X. Now, if we do that, we come back here, we know that we have negative AH minus HG plus, and then so we know it's still 3, 4, 5. So 3/5 HC, and all that has to equal 0. All right. So we go ahead and I put in our numbers. We know that AH is 5625, right? Make sure that's 5625. Yeah. Just double checking. Yeah, 5625. So we have 5625 negative minus HG, which we don't know, and then plus 3/5 of 625, and that equals 0. So we solve and we get HG equal to negative 5250. Okay. So 5250, it's a negative. It means that I guessed incorrectly, that it's not in compression, it's actually in tension. So HG then is equal to 5250, and that's going to be in tension, not compression. Okay. So I have those now. Now let's look at, I want to look at this joint here at G. Now, if we go to G, what do we think we're going to see there? So we know, let's just by inspection, if we have HG, we know HG we found to be 5250, right? So if HG is 5250, then what do you think GF is going to be? Is it going to be the same or different, or what do you think?
It's like it should be the same.
Should be the same, right? Because there's no other X component. And since this is also, remember that this is in tension, so it means it points that way, that points that way, that points that way, and that points that way. So if that's 5250, then what's CG going to be? Does it have any load on it? What do you think? So if each member has to be in equilibrium, let's just look at this here, right? So if we draw that, if we sum our forces in the Y to 0, what do we have? We have CG equals 0, right? So this is what's called a zero force member in a truss. It means that in this loading scheme, it's not supporting any load. So in this, now it doesn't mean it never will. It just means that in this particular loading scheme, because these things are dynamic, they're not always loaded exactly the same, this supports no load. So when you come to C up here, if you were to go from BC, you would have just two unknowns, right? And you would actually find that this was 0, even if you did the calculations. But if we come over to C here, we'll know BC, we know HC, then we would end up with CD and CF. And because the asymmetry of the loading, we can't just assume that this and this are going to be the same as that and that. If it was symmetrically loaded, then yes, it would be. But since it's not, you can't. You'd have to calculate it. You'll see actually a drop off in the loads over here because most of the loads supported on this side. But you could go ahead and go to C. You could sum force X and Y. You could solve for those. Come over to D, do the same. Come down to F, and then finally over here. Oh, you wouldn't even have to go over here because you could come to F and you'd be done. But you can see how once you start in this corner, you can move your way across. But the important thing is this zero force member. Now, if we go back to some of the trusses. If we go back to, here we go. If you look at these here, you notice that like on the Pratt, you notice that right here, that's a zero force member right there, depending on how it's loaded. But as it sits, you know, if there's loads, unless there's no matter how many loads you have on the top, the bottom has to also have a load or a support. So if I put a support under that part, then it wouldn't be. But as it is now, this and this over here are what are called zero force members. If we look at the Howe truss, the only zero force is in the very center right here. If we look over at the Warren truss, quite a few are zero force. Look, this one, this one, this one, this one. In fact, you could, in theory, ask, well, why do you even have all these in there? Because you could get rid of all of them according to this. The same with this one, this little one here, and that little one there. But the thing that's kind of weird is when you have a zero force member, it starts to cascade on itself. So let me see if I can make this. Let me do this. Let's go into PowerPoint real quick and change it so it's not in. There we go. Let's go back to. There we go. All right, so what I want to do is I want to just expand this. So let me do this real quick. Okay, so blew it up because I want to show this. Now, think about this truss. If now we understand that these two members here where I'm pointing the arrow at, we understand that these two have a force, but because there's nothing opposing that, that's becomes zero. Now, if that disappears, let's say that's zero, look at what's left. Imagine erasing this one. You notice how these now disappear? Because now you have the same situation. You have one long line, this and this are the same, and then you have this odd man out that doesn't do anything, okay? So it's interesting when you look at these trusses, you'll have a few where you'll have to look at them and you'll have to say, you know, what are the zero force members in the truss? And I do discuss that in my lecture. And one of the rules is if you have 3 members at a joint and 2 are collinear, then the third is zero force. And so this is a good example right here. You have 3 members at a joint, right? You have this, and 2 are collinear, meaning they're a straight line, then the third must be 0. And they don't have to be at 90 degrees. This could have come in at an angle, but the fact that 2 are straight and the third isn't, then that means they're not. So another way to look at this is, and this is something that I get a lot of questions on. So, but another way to look at this is if you have, you know, a truss like this even, and let's say that we don't care about the rest of it, but let's say it's supported here. Then if it's supported here and there's no applied load over here, then these really don't support any load. They just kind of hang off. And the reason is because we assume that the weight of these members is negligible compared to the amount of force that they support. So these would essentially be what we call zero force members at this point. Now, if I were to apply, you know, something like that, then of course, then they wouldn't be like we saw. But absence of that, or a force, like say we applied a force like this. Now, let's say we did that. Let's say we did apply a force in that direction. If we applied a force like that, then this would be equal and opposite to that. And this here, because these two are, because this has nothing in that direction, this is completely straight to that, this would have to be a zero force member. So it's similar to the idea that if you have, you know, 3 members like this, this has to be a zero force. But if it looks like this, then that's also a zero force. Doesn't matter. Now, if you have 3 that look like this, then you can't know. I mean, you could do the calculations and end up with one being zero force, but you can't just look at it and say it is. And if you have more than 3, then you can't know either. So the rules are pretty simple. You either have 2 where there's no support or force, or you have 3 where 2 are in a straight line. And that's pretty much it. Now, but if they do start to cascade away, like we saw in the truss, let me draw that real quick. Just trying to get on my screen bigger. But if we look at, let's say we look at this one end. Let's see. So it looks something like that. That's the edge of the Baltimore truss. And then it goes up again like this here and so forth. And then it comes across. Sorry. Anyway, and then it goes down. But so if we look at just this part here, you have these internal members. Now, if we look at here, you notice that that then would cause this to be erased. So we agree with that. Now let's say we erase it. If we do that, then we notice that this is in the same situation, right? This and this. So now this one disappears. Now, if we go over here, we have the same situation as that. So this one disappears. Then this one disappears. And finally, this one disappears. So effectively, even though we have all this extra wood in there, unless it's low, depending on how it's loaded, again, if there's just a single load up here, then these internal members have really do nothing. Okay? At least from our analysis standpoint. Not saying they're worthless, they're just not, they're not relevant for us. Okay, it's 10 o'clock. I apologize, I went over about a minute, but I just wanted to get that point across. So quiz Wednesday, we'll cover the moment of inertia, and that's it. If you have questions, see me in my office hour. Otherwise, next week we'll continue and we'll talk about frames. All right. Thanks, you guys. Thanks for coming this morning, and I'll see you soon.
Thank you.
Thank you.